Okay, the next topic that we want to cover is torsion of members with a circular cross section. This is an easy topic because we have worked very hard to get to this point, and we're going to find that there are a lot of similarities between analyzing torsion of circular members and analyzing beams. So what are we talking about? It's when we talk about torsion, we talk about twisting. So that if we, for instance, we are mounting a circular cylinder and we twist it. That's basically what we're doing. And we are going to use the right hand rule. So that use your right hand, curl it, curl your fingers in the direction of the arrow, and the thumb is pointing in that direction. And we indicate that it's torsion by using a double arrowhead. Now what happens is that if we were to, just envision taking this scenario, or when you were a kid, twisting a stick. It's usually something we've all experienced. When you're a kid, you twist a stick, and what do we see as this? We will try to twist the stick until it breaks. And if you look at the way that the stick breaks in torsion or a twisting, what you find is it's the outer fibers of the stick that begin to break, and then as you continue twisting, the fibers near the innermost begin to break. And then what usually happens is you keep twisting and twisting and twisting, but you're not able to break the stick completely. At the end, you have a very thin filament right in the center, and then you pull it and you can break the rest of it. That basically illustrates that the concept is that we're going to find that the shear stress, now we're interested in the shear stress tau, and we find that the largest shear stress happens at the edges. So if I'm going to indicate this with the length of the arrows, we see that the greatest shear stress occurs at the edge, and then as we get closer and closer and closer, it drops. It gets smaller and smaller. So in other words, I'm drawing shorter and shorter arrows as we get closer to the center, indicating that the shear stresses get smaller and smaller as we get toward the center of the cylinder. It could be a solid cylinder, it could be a hollow cylinder. For the time being, let's think of one that's solid. So in other words, we could plot these shear stresses on our cross section, and if you can see what I've drawn here, we have 0 at the center, and then this sort of looks like an inverted ice cream cone in a way, indicating that the stresses get greater and greater toward the edge. Now we've seen something similar to this when we looked at beam bending, in the sense that we had 0 at the center and the greatest at the edges. That was our sigma. And we had that expression, sigma is equal to minus my over I. I did the derivation for the sigma. So I'm not going to, well, put it this way. The derivation for the tau is identical, basically, to the sigma, except the geometry is different. So we know this expression, tau, sigma is equal to minus my over I, and I'm not going to do the derivation, but we end up with, because it's so similar, tau is equal to TR over J. And I want you to memorize that. It's easy. You've already memorized this one. If you've memorized that one, then it's easy to get this one. So it's, minus my over I, TR over J. And of course, we're talking about tau for torsion. And if you remember what these mean, so I'll just review. Sigma is equal to normal stress. M is moment from the moment diagram. Y is the distance from the centroid to the point of interest. I is the moment of inertia about the centroid. That's that equation, and to show you how similar this is, this here we have normal stress, here we have shear stress. M is moment from the moment diagram. T, capital T, is torque from the torque diagram, and I'll show you how to draw that. Y is the distance from the centroid to the point of interest. R is the distance from the center to the point of interest. I is the moment of inertia about the centroid. J is the polar moment of inertia. So these two equations are in parallel. If you know how to use this one, you're going to know how to use this one. It's quite straightforward. I'm also going to say that we're only going to, in this class, look at either solid or hollow circular cylinders. And so to get the J is going to be very simple. It's not going to be a challenge like we had to do with I. J is going to simply be, I'm just going to give you the equation, is that J is equal to pi over 2 times C outer to the fourth minus C inner to the fourth. And I want you to memorize it. What is C? Notice CI is the inner radius. So if I have a hollow cylinder, it's the inner radius. C outer is the outer radius. It's the, again, if I have a solid cylinder, or a hollow cylinder, it's the outer radius. If the member is solid, in other words, the inner radius is 0, then this equation breaks down to pi over 2 times C outer to the fourth. You can memorize this. The reason this is easy to memorize to a certain extent is, one, if you remember, moment of inertia has units of meters to the fourth, or feet to the fourth, or inches to the fourth. So you can remember that this is a 4. The exponent is 4 here, simply by thinking about the units. The only hard part is you need to remember the pi over 2. So this is the equation that we will always use for J. Very simple. Let me also point out that, notice, I didn't make the notation, this is the notation everybody uses, is that C is used as radius. Notice we use the symbol R, but R is not the radius. R is the distance from the center to the point of interest. So don't get confused about those. R, again, is what? Is similar to Y, which is the distance from the centroid to the point of interest. R is the distance from the center to the point of interest. So, like I say, I didn't make up this notation, but C is used for radius. R is used from the distance from the center to the point of interest. Easiest way to do this is with an example. And here's a simple example where I have a cylinder and I am applying 100 pound-inches like that, 200 pound-inches like that, and it's mounted to the wall like that. And my goal is to find tau max in the region AB. This is AB and BC. So tau max in the region AB and BC. This is a solid cylinder. The radius is 1 inch. We're going to use the expression tau is equal to T over J, and we're going to find tau in the AB region and in the BC region, the maximum tau in those two regions. Okay. Here's the solution. The way to do these problems is to use the right-hand rule. And the first thing we have to do is to find the reaction, just like we did with our shear and bending moment diagrams. We had to get the reactions. In this case, we just have one reaction with the mount at the wall. Now, what we're going to do, are using the right-hand rule. This 100, if I curl it, is 100 going to the left. This 200, if I use my right-hand rule, is 200 going to the right. Then we made a cut at the wall. Wherever we make a cut, we have to put a force or forces. Since we're doing torsion, we put in torsion. I don't know which direction this is going. So remember, if I put a letter next to it, it doesn't matter what direction I show. If I put a number next to it, I have to get the direction correct. So it doesn't matter which one, I'm just showing a guess here. And it's pretty simple. I take the sum of the torques in the x direction equals 0. So I simply look at these arrows, the direction they're going, and I write my equation. So what do I see? That's going to the right, so that's positive, so I get TA. That's going to the left, so it's negative, minus 100. That's going to the right, so it's plus 200. All that is equal to 0, just as we've always done. And then I solve for TA. And I get TA is equal to negative 100 pound-inches. And if it's negative 100 pound-inches, then what do I know? That I have to flip the arrowhead around and write 100. So that's what I've done. My TA was to the right. It came out to be negative 100. I flipped the arrow around to the left, and I put in the 100. And then we can easily see that this is in equilibrium. How do I know that? Because I have 200 going to the left and 200 going to the right. It's in equilibrium. Now we're going to draw the torque diagram. Drawing the torque diagram is like a shear diagram, like the easiest shear diagram you've ever drawn. And the sign convention we're going to use is that an arrow going to the left means jump down, an arrow going to the right means jump up. So I start at 0 and end at 0. So I start at 0 here, and I see 100 going to the left. That means I go down 100. Go straight across till I hit the next one. See another 100 going to the left. I go down another 100. Now I'm at negative 200. Go straight across. Then what? That's 200 to the right. That means I jump up. Takes me back to 0. So everybody can draw the torque diagram. This is, like I say, it's like the easiest shear diagram we've ever drawn. So there is our torque diagram. And in the same way that we look at a shear diagram or a bending moment diagram, what do we learn from that? Well, I can see what? Well, where do I have my torque the greatest? Well, the torque is the greatest in this region in here. It's negative 200 in this region. It's only negative 100 in this region. So that's the value of it. We get our J. It's a solid cylinder, so J is simply pi over 2 times C out of the fourth. And since that's 1, since the C, the radius, which is C, is 1, we just plug it in. We get 1.57 inches to the fourth. So I now apply my equation that tau is equal to TR over J. So tau max in the region A to B is going to be T in the region A to B times R over J. Now we have to find the point of interest. Where's my point of interest? Well, I have to find it on the cross section. On the cross section, it's at the very edge. Why is it at the very edge? Because we asked for tau max. And we know that the maximum shear stresses occur at the edge. So my R is what? My R is going to be the distance from the center to the point of interest, and that's 1 inch. So when I plug into my expression, tau is equal to TR over J, we can plug that in using, in the region A to B, what is it? It's going to be the torque in the region A to B times R over J. In the region A to B, the torque is negative 100. So I have negative 100 times my R, which is 1 inch, divided by my J. And I get that in the region A to B, the maximum shear stress is negative 63.6 psi. In this particular case, we don't care about the sign very much, so whether you get it negative or positive doesn't really make much difference to us in this particular situation. But we're going to stick with the negative 6. Well, I'll show you what the sign means a little bit later. For the region BC, then the only difference is my torque in the region BC is what? It's negative 200. R over J are the same. R and J are the same. So we get the maximum shear stresses in those two regions are negative 63.6 psi and negative 127.4 psi. Okay, this one's a little bit more difficult, but I'm going to let you find the tau at the point of interest. I'm showing the point of interest right there. This is a hollow cylinder. I give you the inner radius and the outer radius. The outer radius is 0.6 meters. The inner radius is 0.15 meters. Now my point of interest is where? My point of interest, notice, is 0.4 meters away from the center in the cross section, and my point of interest is excuse me, in this region between D and E. Okay, so what you need to do is pause the video here and work this problem as well as you can. Okay, I'm going to assume that you've paused the video. I'm going to show you the solution. First thing I do is find the reactions like we've always done. So I use the right-hand rule. This 800 is to the right. That 500 is to the left. That 1200 is to the left. This 200 is to the right. And then here's my wall, and I make a cut there. So TE, it doesn't matter what direction I show it because it has a letter next to it. I look at this free body diagram and I take the sum of the torques in the x direction equals 0. And so this is what to the right, so it's 800. To the left, so it's minus 500. To the left, it's minus 1200. To the right, it's 200. To the left, I go minus TE. I solve for TE, and I get TE is negative 700, which means, again, to show it on our final free body diagram, I have to flip the arrow around and show 700, so it's to the left there. I draw it to the right, positive 700. I double check to make sure I have equilibrium, and what do I have going to the right? I've got 800 plus 200 plus 700, that's 1700 to the right. To the left I have 1200, 500, 1700 to the left. So indeed it's in equilibrium. I then look at this from our final free body diagram to draw the torque diagram. And remember, if it goes to the right, I go up. To the left, I go down. So start at 0, I see 800, I jump up 800. Straight across, down 500. Straight across, down 1200. Straight across, up 200. Straight across, up 700. And I get my torque diagram starting at 0 and ending at 0. And notice my point of interest is in this region, which means I'm in the region where the torque is negative 700. So when I apply my expression tau is equal to TR over J, I use the negative 700 for the T. That's this value, torque diagram. The J is pi over 2 c outer to the 4th minus c inner to the 4th. That was all given. And I get J is 0.203 meters to the fourth. So I get the 700, I get the 203, and then what I've been given that the point of interest is 0.4 meters from the center. And I get my tau, negative 1381 kilopascals. Very straightforward if you've done far more complicated problems than this. Okay, I'm going to stop there.